Hello everyone. So in this video, I'm going to show you how to calculate the terminal velocity of a raindrop. Um, so the terminal velocity of a raindrop is how fast the raindrop is falling after it comes to full speed, which is the speed of most raindrops because raindrops have typically been falling for a while by the time they get to the ground. So we could just call this how fast do raindrops fall? Um, and in particular, we're going to look at the speed of a 1 millimeter diameter raindrop. That's a pretty common diameter for a raindrop. However, there's a distribution of sizes of raindrops. So there are bigger raindrops and smaller raindrops, and they will have correspondingly different sizes or different speeds. But we're looking at a typical 1 millimeter raindrop. Okay, so the first thing we're going to do to calculate this is we're going to find the mass of the raindrop. So we're finding the mass of the raindrop. Well, one thing we can use is we can use the density of water. Rain is made of water, and water has a density of 1 gram per cubic centimeter. So we got a density, and we can calculate the volume of a raindrop. The volume, we can assume the raindrop is a sphere, so 4/3 pi r cubed is the volume of a sphere. So we can calculate the mass. Mass equals rho times volume, because rho is mass per volume. So we can calculate mass that way. So we can calculate it as rho, which is 1 gram per centimeter cubed times 4/3 pi. And then r is, 0.5 millimeters. The diameter is 1 millimeter, so the radius is 0.5 millimeter cubed. Need to throw a conversion factor on there of, there's 1 centimeter per 10 millimeters. And we're going to have to cube that so that we can cancel out our millimeters here. We cancel out our millimeters and our centimeters, and we're left with grams. So putting that together, we have, you do this math, if my calculations are right, I get about 5.02 times 10 to the minus 4 grams. So raindrops are not particularly heavy, or not particularly massive. 5.2 times 10 to the minus 4th grams. Okay, that's a raindrop for you. Okay, so now question number 2. Use pi r squared to calculate the cross-sectional area of the raindrop. Why do we want to calculate the cross-sectional area? Well, drag is going to depend on the cross-sectional area. If it's a bigger cross-sectional area, it's pushing more air out of the way, has more drag. So it's important. So A is equal to 1/2, pi r squared, but r is d over 2, so that's 0.5 millimeters squared, and according to my calculations, that's like 7.9 times 10 to the minus 7th meters squared, after you do the conversion from millimeters to meters. Okay. Number 3, we are told to find the density of air, or look up the density of air. So if you look up the density of air, it depends on the temperature outside. But for reasonable temperatures, remember this is outside when it's raining, reasonable temperatures, you get a rho of about 1.2 kilograms per cubic meter. It's rough density of air at roughly sea level and typical temperature outside. If it's a little warmer, it'll be a little less. If it's a little colder, it'll be a little more. But there you go. Okay, so that's that. So that was 3. Now on to 4. 4 asks us, let's see. 4 asks us, what is the viscosity of air? So you can look this up on Wikipedia. You can look this up in the textbook, many of different places, and you'll find the viscosity of air is equal to 18.5 micropascals times seconds. If you see somewhere that tells you that the viscosity is some other number that's in a different units, that's a different type of viscosity called the kinematic viscosity. Ignore that. You want this type of viscosity. This is the normal viscosity. It's the one, also known as dynamic viscosity. This is the one you want, and it's 18. Write that a little better. 18.5 micropascal seconds. We can also write that as 18.5 times 10 to the minus 6 Pascal seconds. Okay, so that's the viscosity of air. And it's the viscosity of the air that matters for drag, because as the raindrop falls, it has to push air out of the way. It says drag as it goes through air. Okay, number 5. Okay, so now we come to the tricky part. This is where we use terminal velocity. So in class, we derived that to find terminal velocity, you cancel out force upward, drag force upward with a gravity downward. There were two types of drag. We are particularly interested in this equation here for a turbulent drag. So we're going to write this as V is equal to the square root of 2mg over c rho a. If you don't remember this from class, it's because it happened on Monday, which is after the recording of this video. So if you're watching this video before Monday the 19th, well, go back and well, you can wait for it. We'll cover this in class. Okay, so that's our velocity. Let's calculate it out. 2m. So our mass, we calculated our mass up there was 5.2 times 10 minus 4 grams. G is 9.81 newtons per kilogram. Actually, let's make that meters per second squared. Same thing. Meters per second squared. We're going to divide by c, and we're told that c is 1.5. We'll talk about why that is in just a moment. 1.2 kilograms per cubic meter for the density of air that you're moving through. And then finally the area, cross-sectional area, which is our 7.9 times 10 to the minus 7th meters squared that we have right up here. See, do we need to do any unit conversions? I think we need to do a, there's 1,000 grams per kilogram, if you want to put that one in there. And is there any other unit conversions we need? Okay, let's try it. Let's check out our units. So grams cancel with grams, kilograms cancel with kilograms. We have let's see here. So this meters cubed comes up in the top, gives us meters to the 4th. Divide by meters squared, which will give us meters squared. So we can actually do it right. Cancel with that, make that down to a, how do I do this? 1, 2, yeah, we'll just do it this way. Cancel that and that. So then we'll end up with meters squared per second squared inside the square root. You take the square root, you get meters per second, which is good because we're looking for velocity. You stick this all together, you should get a number around 2.7 meters per second. So there you go. That's how fast a raindrop falls. 2.7 meters per second. Okay, and that okay, so that's that. But we still haven't talked about where the C came from, and to do that, I'm going to discuss the answer to question number 6, which is what is the Reynolds number of the raindrop? Number 6. What is the Reynolds number? So number Reynolds is equal to 2 rho VR over the viscosity, viscosity eta. Okay, so 2 are rho, and this is the rho of air. It's the thing you're moving through, 1.2 kilograms per meter cubed. V, our velocity, we just calculated, that's 2.7 meters per second. R is our diameter, which is 0.5 millimeters, divided by our viscosity, which is 7.9 times 10 to the minus 7th meter. Sorry, wrong number. I want our viscosity, which, where was our viscosity? Oh, right here. 18.5 times 10 to the minus 6th Pascal seconds. Let's do some unit conversions here, see if we can get, if this is the right units. Okay, we're going to need to convert 1,000 millimeters to a meter. Pascal is equal to a Newton per meter squared, and a Newton is a kilogram meter per second squared. Okay, so now we get to do the great canceling of, we should have some fancy name. So Newton, Pascal, second, or wait, no, those seconds are on this, both on the bottom. This second cancels those two. This kilogram cancels that kilogram. Millimeters, meters cubed, and where is meters. Okay, I don't know if I've ever canceled that many things. That gives you well, no units at all, which is kind of cool because Reynolds number doesn't have any units. If you do all that multiplication together, I believe that you should get a number of around 170, or 1.7 times 10 to the 2. Okay, so that is the Reynolds number. So that completes the problem. Now I just wanted to do a little bit of a discussion here of where we got our coefficient of drag, this 1.5 there. I just gave it to you in the problem, but where did I get it when I made up the problem? Okay, so if you look at this table here from NASA, this plot here from NASA, they have a plot of Reynolds number on the bottom and coefficient of drag on the right here. So if you look at, so 10 to the 2 is right there, so 1.7 times 10 to the 2 is somewhere around here. And so if you go up there, okay, maybe it should have been a little less than what's somewhere up there. So it's around 1.5. Maybe it should be maybe 1.3, somewhere up there. Coefficient of drag is the drag on the sphere. So that is how you find the velocity of a raindrop. Thanks for watching.